Glad I've got the studded tires on the bike. Okay, so let's. So what we just did, I just gave one little lecture with an intro explaining the course. Now what we're going to do is get into the week 1 assignment, and that was it's just kind of a warm up, looking at energy that is in some sort of daily household items, and I'll just repeat the one that Sean did. So energy. Let's call it Learning Unit 1, Energy in Household Items. Put this guy over here, and I'll just call this I'll just call it truck, right? Truck fuel. And I like the way. I like the way Sean did this, so I'm just going to stick with it. No reason to mess around with it too much. But like I said, I'm going to first get out my pencil paper, in this case my virtual pencil paper. And so the first thing I'm going to do is, this will be energy in fuel tank. And so you can start out in a couple different ways. And what I usually do, and this might help too, is just to draw a picture. So here's the tank in the truck. It's partially full. Most fuel tanks are going to be anywhere between 10, up to 30 gallons, depending on how big the vehicle is. So we could kind of fall somewhere in the middle and just say 20-gallon tank. And I'll just start off with a little equation, and we know that the energy, and I don't know if you guys do this in algebra or not, but this is just how I'm gonna write it out. Energy is it's going to be a function of both the volume. So the volume is just the amount of fuel, and let's see, what's a good symbol to use. I wanted to use another symbol for energy density.
Weird P?
We can use a rho for now. The weird P will do just fine. Okay. So the question is there anything else I need to know to determine how much energy is in the tank? Obviously, the more there is in the tank and the more energy there is per unit volume, the more energy there's going to be.
Right.
You might think, well, gosh, what about the temperature? Well, maybe a little bit. What about the grade of fuel? Well, sure. And so you might in your ponderings, say, oh gosh, maybe the energy is also, it's a function of the volume, the energy density, the temperature, question mark, I'll just write G for grade, question mark. And, when you think about this, the answer is going to be yes. If the stuff is hotter or colder, it's going to have an effect. If, obviously higher octane fuel is going to be better. But in general, and again, this is, putting your engineering thinking cap on, these two factors are going to be negligible. So we'll just kind of say those are about zero. And if you want to explain that, there's room to do so. You can just sort of say that right here. Fuel in gasoline tank or diesel tank, whichever one you're doing. Assume only a function of volume and energy density. There you go. So we just kind of you put your thought process out on the page. Okay, so I'm still still on the pencil paper. We've determined that it's just the volume and the energy density that's going to matter. So, and we can pretty much make up this number, 20 gallons. So let's go out and just take a look. Might even be something in here. Well, no. This is also something worth mentioning. The embodied energy is different from the energy density. The embodied energy is how much energy it took to actually create that material, not how much energy you get from using it. Two separate things. So let's get a new deal going here and do energy density. I love going back to this little chart. The neat thing about the chart is you can measure energy density either on a per volume basis, so here's megajoules per liter, or on a per mass basis, so megajoules per kilogram. And somewhere in here, there's ethanol, there's E85 gasoline, and you can see that E85 gasoline is less energy dense, both on a volumetric and on a mass basis. If we pop up here, you can see that gasoline is more energy dense on a mass basis than diesel on average, but less energy dense on a per mass basis. And if you've dealt with both fuels, you've probably said, yeah, diesel, it's a little stickier, a little syrupier. Just the molecules are a little more packed in there than in gasoline. So intuitively, that makes sense.
Not as refined.
Yeah, right. Not quite as refined. So, Sean, you have started with BTUs, and that's fine. You probably found it somewhere. What you might do, yeah, it looks okay. So that's great. It looks like you did go up and look it up, on a Wikipedia site. I'm gonna just for grins, I'm gonna use megajoules instead. You can start anywhere you want. There were no instructions saying where you have to start, so don't worry about that. So now let's look at gasoline. I'm just going to call that 34 megajoules per liter. Okay. And I'm making it a little bit hard on myself because I'm going to work in liters, but I'll convert that to gallons. So I know that the energy is going to equal the, and I'll write it this way, the energy density times the volume. It's the product of those two things. And I'm also going to write out the dimensions, and again, this will get us back into that engineering technology. The dimensions that I'm going to use for rho are joules per, actually no, let's back up one quick second. The dimensions I'm going to use are energy per volume. The dimensions that I'm going to use for volume are just volume. And if you want to get, picky, you can say, well, this is, meters cubed. This is meters cubed. This is, kilograms, meters squared per second squared, etc. But you do not need to dig down into all of these weeds here, just to let you know. At the end of the day, though, when we multiply density, which is energy per volume, by volume, we're going to get energy. That's first thing to know. And I'm going to start with density as joules per liter, or joules per gallon. And then ultimately, well, I guess I'll write one more. I know that I'm going to end up with kilowatt hours per gallon, because as it said in the notes, this is SI units, and this is imperial units. I'm going to use the word imperial, IMP. So it's a little bit of a mixture. So that's density. And then for volume, we'll start with liters, but then we'll convert it to gallons. Okay, so here we go. I've got the, and if you guys want to do it a different way, that's fine. I'm going to show you my little energy accounting methods. We were just out here at energy density, and we came up with 34 megajoules per liter. And when you think that through, if you remember back to NRGY 101 and 102, each of us uses 10 megajoules of energy metabolically. So when you see 34 megajoules, you're like, oh, so that means if my body could burn gasoline, I could run on 1/3 of a liter of fuel per day. And it's like, well, okay, it's pretty high. I could believe that. Yeah. What are the energy drink? It's a pretty high density energy drink. So again, so 34 megajoules per liter is what I'm going to start with. And now I know I need to get from megajoules to kilowatt hours. And by the end of the semester, you guys will be doing this in your sleep, I promise you. But what I need to do is put megajoules in the denominator, and I need kilowatt hours in the numerator. So again, let's just pop out 1 kilowatt hour 2 megajoules. Google's pretty fancy these days. It tells you the answer before you hit return. So 1 kilowatt hour is 3.6 megajoules. Okay, so one kilowatt hour. 1 kilowatt hour is 3.6 megajoules.
Wait, don't we want to do how many kilowatt hours are in 1 megajoule?
Did I get that backwards?
Do we want to get rid of megajoules so we end up with kilowatt hours?
We do want to get rid of megajoules. 1 kilowatt hour is 3.6 megajoules. Let's get back here. I guess so here's your question. I think I know what you're asking me. 1 megajoule to kilowatt hours. Okay, so 1 megajoule is 0.2777 kilowatt hours, right? Is that where you're going with it?
Well, I mean, just to cancel out units.
Yeah.
Oh, never mind.
Yeah, but I guess what I'm saying, no, it's a valid question. What I'm saying is it should be the same difference.
Right.
Because, you're right. I could put a 1 down here and the 0.277 up there, the fraction's going to be the same. So let's just convince ourselves of that. So if I do 1, or no, there's even a fancier way to do it like this. Let's see, clear. Delete. So 3.6, if I just hit the 1 over x button, there's your 2.7.
Gotcha.
So, yeah.
Same difference.
Exactly. Another point I think is really, really worth making right now, I've made it in a few other courses. In every one of these problems, you're actually solving 3 problems at the same time. You're keeping track of the algebra, or I shouldn't even say the algebra, the arithmetic, which is just the number that you're working with. You're working with the second problem you're solving is the power of 10, and then the third problem you're always solving are the units. And so what we just saw there is like, okay, are we really keeping track of our units? And they're related, and they're all wrapped up in there. We've got the number, got the power of 10, and then we got the units. And every single one of them has those 3 components. 3.6 is the number, Mega is the power of 10, joules are the units. 1 is the number, K is the power of 10, watt hours are the units. Okay, super. Good question. All right, so now the next, so we know we want to put this in kilowatt hours per gallon. So the next thing is to get gallons and liters lined up. I know it's 3.8, but I'll just say 1 gallon to liters. Let's just say 3.79 for 3 significant digits. 3.79. Now I know I need liters up here. I need gallons down here, and I'm going to use GAL because just G means grams. So 1 gallon is 3.79. Is that what I just said?
Yeah.
Okay, 3.79. And then really the last thing to do here is to go back up, and what did I say? I've got a 20-gallon tank.
Mm-hmm.
Okay, and then 20 gallons. All right, now we should be all set. We should be ready to rock on this. Let's just see. The megajoules are going to cancel. The liters are going to cancel. The gallons are going to cancel, and all I'm going to be left with are kilowatt hours. So if we go back to Sean's example here, he wrote, kilowatt hours per tank. Perfect. Kilowatt hours. And I guess if I wanted to be even more correct, energy per, tank. And even here I could even write, 20 gallons per tank. Calling a tank a unit. Very important. Okay, now from there, it's more or less a matter of just running the arithmetic. So let's bring up the calculator. Everyone's got their own favorite way to do things, but I'm just going to start right across the top, and they'll go across the bottom. So I'm going to start with 34. I'm going to skip the times 1 part. Times 3.79 times 20 divided by 3.6 equals. So I'm looking at 716 kilowatt hours. Tell me what you get, Joe. It's always good to...
Same thing.
Same thing. Okay. So 716 kilowatt hours. Let's come down here and write that out. Equals 716 kilowatt hours. Now, oops, I'm gonna rewrite that a little bit because I want to be kind of picky about this. This should be a lowercase k for kilo, uppercase W for watts, and lowercase h for hours. That's the proper way to write it. Let's see how that stacks up against Joe's answer or Sean's answer. Yeah, he had a bigger tank, so he's got a little more energy. It's on the right order of magnitude. Now, when we get further into the course, and in fact, we were just doing this in 243 this morning. If a house runs at a kilowatt, how many hours can your truck run your house? Well, 716. And we could even say, oh gosh, how many days could your house, your truck run your house? Well, let's see. We can just say 716 divided by 24 equals. So if you hooked her up right, and didn't have any losses, your truck could run your house for a month. So we'll get into that a little bit more. So now that we've done it on paper, let's just put it into the Excel spreadsheet and see how we do. And so I'm going to start off with 20. This is going to be gallons per tank. You might also, and here I'm gonna do both ways, not to confuse you, but just to say, usually I would write it out like this. I would write gallons, or I would write it like this: fuel, and then I would put the units, gallons per tank. So you're naming what it is you're talking about. In fact, I'll do it that way. Just you've already seen the way Sean did it. So fuel is gallons per tank. You know what the units are. And now I'm going to write energy density. And I'm going to write this as megajoules per liter. And if you want to get fancy, and I'm not going to say don't get fancy, you can take this and turn it into take that L and make it some kind of script. Otherwise, it looks like a 1. So pick something that looks like something else. And then we've got that at 34. And now we're going to do kilowatt hours per megajoule. And we can write this as given. We can write this as conversion. We can write this as conversion.
Do you want us to put cite where we got these?
It'd be nice.
Okay.
Yeah, and then you can go, because that way, do it for my benefit, but do it for your own too. If you go back and like,
Sure.
oh, was that an unreliable source, or did I just miscopy it?
Right.
Yeah. Kilowatt hours per megajoule, and then we're going to have gallons per, or I'll do it like this, liters per gallon, conversion, and now we're going to do, and I think that's all we needed. Energy in the tank, 2 conversions, fuel in the tank. Okay. Kilowatt hours per megajoule. Did I do that right, or is it?
Yep.
It's 3.6 megajoules per kilowatt hour, right?
Right.
So one way to do that, and I know it's 3.6, and rather than do the math, I'll just say equals 1 divided by 3.6. There's the number we had before. And you can leave those significant digits there if you like, or you can come in and do a control 1 and hit number and just give it one of those. Okay, liters per gallon, we know that's 3.8, or no, 3.79. So we're just, being precise here and just using 3 significant digits, just precise enough. Okay, and then we're going to have energy per tank. This is going to be in kilowatt hours. This will be answer. Okay, so I know that in this cell, this is just going to equal, and the way to, and I know I didn't type this out exactly the same way I did on my little notebook, but again, same difference. As we just said, it's a matter of just keeping multiplication versus division straight in your head. Nothing too crazy. Let's get both of these guys on the same sheet now so we can see where everything's coming from. Scroll down a little bit here. So equals, and I'm just going to start at the top, and I'm going to click on this cell, 20, because I know that's in the denominator, times 34, because I know that's also in, or I think I said denominator, numerator. Those are both in the numerator. And then times, I know that 3.9 is also in the numerator. Now the question is, what do I do with that 0.278? Do I divide it or do I multiply it? Well, if the 0.278 were the 3.6, I would divide it, but instead I'm going to multiply it. Hey, what's going on, Chris? Good, man. What's going on? Oh, bummer. Well, okay. You know, I'm YouTubing these. Maybe just stay home and take it easy, and we'll see you next week. Yeah, the YouTubes will be there tonight. Okay, Chris. All right, bye. Okay, so there's my answer, and I think that matches. Sorry to interrupt course, but it was for a student who was dialing in. Chris said he's here, but he's not feeling well, so I don't want to risk him getting everyone else sick. So, okay, 216. Let's see if Excel can get the same thing. Again, I'm going to do Control 1. I'll go into number, and I'll knock those 2 decimals off, and there we go. So, I'm going to make that yellow. That's just kind of the convention. Conversion, I'm going to make that gray, or maybe blue. Blue's a little bit happier. This is also conversion. This is also a conversion, and then there's your answer. You can put in red. If you wanted to, if you want to do something else, this in some way is also a. It's not really a conversion so much as a constant. Or a physical variable. So if you want to do something different with that, you can. The conversions. These are just one. This is just energy to energy. This is volume to volume. This is more energy to volume. The units are different. So this is more like a constant. Gravity is measured in. Meters per second squared. The units are mixed. So if you want to use those 4 different colors, this tells your user, and eventually this user could be you, because you're hopefully this course sends you out with some nice tools. You say, oh, I got 35. Well, there you go. That's the nice thing. Once you've set the thing up in Excel, it just works for you time and time again. So 40, okay, super. Oh, I got a little tiny tank left too. Oops, only 72 kilowatt hours. So that's the that's how to run that system.
Did my car? It's an 8-gallon tank.
8-gallon tank. Okay, yeah. So
do you want the? Let's see. I just remember sitting in on some of these classes that have the equation visible next to the answer.
Oh,
like C this times C that.
Yeah, it wouldn't hurt.
I don't know how to do that.
Okay, so let's say we do want to write this out. We can do E equals RV, for example. Nice thing to do would be and this is again, once you get the hang of it, it's kind of a pain the first time. But you can turn that into Times New Roman. What I would really like to see, and this I'm hitting the Shift key and 2 back arrows, and then I'm going to italicize those guys. Shift key, back arrow, italics. Now we know what energy is, and you could just just say down here, E, oops, E, energy, rho, energy. Density, V, volume, right? These guys can all become Times New Roman, italics. Okay, now you're like, what the heck? Why is that an R when it's supposed to be a row? Shift backspace, symbol.
Oh.
Symbol. So fancy. Yeah. So all of the, and if you're like, gosh, I don't know what that letter is. Well, here's a really super easy way to do it. Hop into Microsoft Word. A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. Hopefully. Not a word, but useful. Yeah, that's right. So I'm going to copy it. I'm going to paste it. And I'll paste it again. And what I'm going to do with this one is turn it into a symbol. So there's the Latin alphabet turned into the Greek one. So alpha, beta, gamma, delta, epsilon. Phi. Actually, I think that's chi. Sorry, alpha, beta, chi, delta, epsilon, phi, gamma, eta, iota. Come on, Leighton. It's not Omicron. I think that's just a different phi. Kappa, lambda, mu, nu, omicron, pi, psi, different row, sigma, tau, nu, not maybe a different nu, two different types of omega, xi, psi, zeta, I think. You can also take them and capitalize them and then turn them into Greek with symbol. And there's the, not exactly the Greek alphabet because there's only 20 symbols, but that's what they look like capitalized. Okay, so that's how you would put this in there. There might be a way.
I remember last year they were having them display the equation as it's like C11 times C10 times.
Oh. Yeah. I'm not going to require.
It seems like you can just click on the square and it's up there in the dialog box.
Yeah. I guess if you wanted to, no, I wouldn't do that.
Okay.
I'm going to click here, and I can see what it is.
Right.
And you're going to turn this into me like, well, look, sorry, you divided when you should have multiplied. But yeah, don't crowd this, because what'll happen if you're like, C12 equals C8 times C9 times C10 times C11. If you come in and change something, like insert some cells, then it's all wrong.
Right.
So don't, yeah.
Okay. Good.
But yeah, this would be a handy little thing to have. Have that out the side. Excuse me. So yeah, you've got your equation, you got your labels, everything is labeled with units, and we're done. So yeah, so that's
I'm doing it right then.
hopefully over the first little hurdle. Yeah. So to answer your question, Sean, it looks like that first problem is correct, and it looks like the formatting is just fine. Keep doing what you're doing, and we'll get these guys, graded for accuracy once you send in your Excel spreadsheets. All right, let's take a break. Fuel up, 30 minutes, perfect. And we'll get on to week 2.